Can people hear me back there? Yep, super, lovely. Good evening, everyone. Lovely to have all of you joining us this evening for this quarter's Space Institute event. The Space Institute, which I'll talk about in a second, holds these events almost every quarter. The last quarter we held one on space medicine, which was extremely entertaining because you saw something which doesn't normally get relayed on television screens, which is astronauts being sick. So if you missed that, don't worry, other opportunities will come up. Today we are going to talk about the search for life in the universe. And the primary mission of the Space Institute is to discover, educate, and innovate sustainably. So what do I mean? Discover new phenomena in the universe. Educate, which is train the next generation to be good stewards of society and the planet. Innovate, come up with new technologies with which you can solve problems on Earth as well as in deep space, and do this sustainably because we don't want to do all these things while destroying the planet. So that's the primary goal of the Space Institute, and there are 8 departments involved with this, and I'll show you this in a second. Me and Jacob Bortnick, and Jacob is right there, together help steer the Space Institute and have the 8 departments work together. Basically, the faculty from each of these departments are involved in a number of research areas. And those are the research areas that the faculty are involved in. So there's a lot, as you can see. There is planetary exploration, which is going to the moon, going to the moon, Mars, other solar system objects, finding water worlds, where are there oceans in the solar system, monitoring space weather, the impact of solar storms on satellites, as well as on the human body when you're in the International Space Station. In addition to those, there are more subtle things like remote sensing, studying the health of the Earth, metasurfaces, making tiny little devices which are a couple centimeters thick, which can solve problems like finding fires on the surface of the Earth in a faster way. On using quantum sensors to do things smaller and more nimbly than has historically been possible. Or doing magnetometry, which is studying how the Earth's magnetic field is changing with time and studying the impact of that on humans on Earth. So we work in this amalgamation of technologies, pure science, and applied science. And if you want to hear more about these research topics, please go to this website and check it out. But today, we are going to focus on the search for life beyond planet Earth, in parentheses. And we're very fortunate to have some of the deepest thinkers on this topic here at UCLA today. So let me introduce each one. We have Jonathan Nanine, who is the chief scientist at JPL and a professor at Caltech. A long time ago, he got his PhD from Caltech, and then he went away to Cornell for a long time. And he's sitting right here. And then in the last year or so, I don't know if it was the climate in Southern California or the excitement of the scientific research in Southern California, which enticed him back. And so he's now right across town. We have Professor Bjorn Bennecke, who got his PhD from MIT, and less than a year ago joined us here at UCLA. He's doing pioneering work with the James Webb Space Telescope. In between, he was a professor at Montreal. So notice the theme here. People go off to close clients, and we bring them back to home. We have Professor Hilke Schlichting, who's also the Associate Dean for Research at UCLA. She got her PhD from Caltech and then was a faculty member at MIT before she was enticed back to be at UCLA. We have Jean-Luc Margot, who has been here for a while, but he got his PhD from Cornell. And he was a professor as well at Cornell. And again, he was enticed back to Southern California. And we have Emily Cardarelli, who got her PhD from Stanford. And you may have seen her name in the news recently because some of her research was involved in finding biosignatures or potential biosignatures on the surface of Mars, which she will talk about. So we're very, very fortunate to have this breadth of knowledge and the depth of knowledge at the same time in this hall. So we hope that after stimulating your appetite outside, we can stimulate your intellectual appetite in here. So the agenda for today is a 45-minute talk by Jonathan on Mars sample return to Enceladus and beyond, finding habitable environments and life across the solar system. And then we'll have a 30-minute panel discussion moderated by Emily between Bjorn, Hilke, Jean-Luc, and Jonathan on the different ways in finding life as well as technological signatures of life. And then we'll have a 15-minute audience Q&A, and at 7:30 we will wrap up. So without further ado, over to Jonathan.
Thank you very, very much, Ranga. It's a real pleasure to be back here at UCLA and to be here at this marvelous institute. So when we look out in the skies at the heavens, I think one of the questions that comes very frequently to most of us is whether we're alone in that vast cosmos, whether there is life elsewhere in the universe. And one way to approach that question is to try to understand whether life began in multiple places here in our own solar system. That's a particularly attractive way to do that, in my view, because we have the opportunity to actually sample places in the solar system where life could potentially exist, what are called habitable worlds, and maybe actually identify life forms. So there we go. Point it that way. All right. So in addition to the general question of whether life occurs elsewhere, we also want to understand how difficult it is for life to form, how special we really are. And there's a curious thing about looking out at the universe and looking at the marvelous chemistry that goes on. So in this particular diagram, there's on the top, I've put primordial chemical diversity, and that is all of the chemistry that astronomers can observe in interstellar clouds, that we can observe in some atmospheres of extrasolar planets and so forth. There's a tremendous diversity of chemistry that goes on there. When we look at our own home world, we see that organic chemistry on the Earth is dominated by biology. So organic chemistry is chemistry involving carbon and hydrogen compounds. It doesn't imply life. You can have organic chemistry without life. But the organic chemistry, at least on the surface of the Earth, is vastly dominated by life. And yet, there's this tremendous uniformity in the biochemistry of all life forms on the Earth. All life on Earth uses the same basic monomers, the same basic components to build structures, to accelerate or control reactions, to process information, and also energy. And so somehow in the evolution from non-biology to biology, we went from chemical diversity to biochemical uniformity, and yet tremendous morphological diversity. The basic tools of biology have, over 4 billion years of time on the Earth, evolved so many wonderfully different kinds of life forms. Somewhere in between, there had to have been, in the evolution at least of the Earth, a time when there was a chemical selection that occurred, and certain kinds of reactions, certain kinds of materials were preferred over others, to the point where eventually there was some sort of a bottleneck and life began. And today it's not understood how that happened. The steps leading toward the origin of life are not completely filled in by far. And so the question is, how did that happen? Can we discover the answer in a lab? Maybe so. Can we discover the answer in computers? Probably not, but as a theorist, it's very enticing. But I think we can potentially discover it if we can find life elsewhere in our own solar system and ultimately study it and see if it went through that same bottleneck or a different kind of bottleneck than the one that the Earth did. So from a scientific point of view, it's very important to go to places where life might be or might once have been. And a premier such place is Mars. So for Mars and other places I'm going to talk about in the solar system that might contain life, first question is, are these places habitable, or were they habitable? Can they or did they once support life? And for the Earth has been habitable for 4 billion years. It's had liquid water on its surface, despite the fact that there have been tremendous environmental changes. For Mars, on the other hand, the evidence from 50 years of spacecraft exploration is that Mars was habitable. It could support life in the first billion years of its history. It cannot do that, at least at the surface. It cannot do that today. But what is left behind are the clues to how those changes occurred, how Mars went from being a habitable world to the world that we see today. And then I'm going to highlight here Enceladus, which I'll talk about later, a little moon of Saturn with a plume of gas and ice pouring out of its south pole that has a liquid water ocean in its interior that, as far as one can tell from data from spacecraft missions, that ocean can support life today, but we don't know how long that ocean has existed and whether it's stable and whether it freezes up with time or just melted. So the exploration of the planets, in addition to looking for habitable environments, potentially also tells us whether life is present. And that's a very, very difficult part of the search. And the reason is that particularly on Mars, the evidence for that life, if it existed on the surface or near the surface, is billions of years old. And the ravages of time, if you want to put it that way, radiation on the surface, disturbances and so forth, and just plain aging of those materials have obscured that evidence. And so it's kind of remarkable, actually, that even today, rovers such as the Curiosity rover can dig only a small distance into the soil, the surface of which is highly sterilizing because of UV irradiation, and actually find the kinds of molecules that one might expect if life had been present. This doesn't mean that life was present, but those molecules potentially could have been from life. And in particular, for the Curiosity rover, the instruments on board identified long-chain hydrocarbons, or fragments thereof, which might have been parts of cellular membranes. And by the way, you'll see a couple of selfies of the Mars rovers, and it's probably familiar to most of you now that there's a camera on an arm that can be commanded to move around, take pictures of the rover, and then back on Earth, the arm itself is artfully removed by Photoshop so that it looks like someone has taken a picture of the rover, but it is a selfie. And this is a rover that has been there since 2012, so operating for a long, long time. And then, as I'll talk about a little bit later, places like Enceladus, there's evidence on Enceladus for all of the essential elements required for life, except maybe sulfur. In particular, the discovery of phosphates is quite spectacular. So I want to just dwell on Mars a little bit for a moment and tell you why it's important not only to analyze samples in place, but also to bring them back to the Earth. So this is a composite of a number of low-angle images from orbit of the region that is being explored today by the rover Perseverance Mars rover, which was built by JPL, is operated by JPL, and has as its goal to return samples back to the Earth. The landing site, or the area around it, is pretty remarkable. And what you're seeing here is the western edge of the crater in which Perseverance landed. It landed somewhere down below the scene here. This crater is called Jezero Crater. It's about 50 kilometers across, give or take. For scale in this image, this little crater here, called Belva, is about a kilometer or so across. And there are a number of remarkable things that happened in this crater early in the history of Mars. And we don't know exactly when. There are rough estimates for it. We want to know exactly when that happened. So the first thing that maybe strikes you is this feature here, which is called a delta fan, that looks very much, has the shape of a remnant river delta. And on its margins, you can see a variety of, you can't see it in this image, but when the rover images it up close, there are boulders and layers that indicate varying degrees of flow of water that led to the deposition of this material in this crater billions of years ago. This is literally a pile of sediments lying on the crater floor. The crater floor seems to be igneous, so there was some volcanic activity. And these sediments were fed to the crater floor, the western end of the crater, by a river system, or river channel, which is now dry and snakes out over here off to the northwest. And that river channel, the water flow at some time early in the history of Mars, breached the wall of the crater, deposited material in the crater floor as the water flowed out of the channel, spread out, and slowed down, allowing the sediments to drop out, just as they do in a river system on the Earth, where the Mississippi River, for example, dumps out into the Gulf and deposits its sediments. And then actually there's evidence on the other side of the crater for a similar breach, and so evidently the entire crater was filled at one time with water. So sampling that material is really important because it's in that material, either in the delta feature or in the channel, where there might be evidence that biological activity had once occurred. But there's also great stuff here for planetary geologists, because the crater wall itself is created by the impact that generated this hole in the ground, an asteroid, fragment of an asteroid, 5 or so kilometers across, hitting the surface. That excavates material from deep below the surface of Mars and dumps it onto what becomes the crater rim. And by sampling that material, it's possible to sample material from below the surface, and also with what's called radioisotopic dating to determine when that impact occurred. And then Jezero crater is actually a crater within a much larger impact basin, the Isidis Basin, which is the result of what is called by planetary scientists a giant impact, which had to precede the formation of this crater and probably occurred very early in the history of the solar system. And so there is beyond the crater rim megabreccias, which may perhaps tell us when that large impact occurred, the giant impact, and also something that size could have caused water deep underground in Mars to liquefy and create potentially a hydrothermal system. So the great thing about a rover is that it can drive around and sample all this material. It is, I would say, even though we're talking about the origin of life, as important as that is, just to be able to collect samples from a place like this where volcanic and impact activity occurred, because it's possible to get the absolute dates from radiochronology of all these events. When the Apollo missions went to the moon in the late 60s and early 70s and brought rocks back to the Earth, and they were analyzed in geochemical laboratories like those here, the ability to determine when events occurred, when impact craters occurred on the moon, provided an absolute chronology to the first few 100 million to 1 billion years of the Earth-Moon history. That's one of the greatest contributions of the Apollo missions to science. It was crucial to understanding the events that went on in the early history of the solar system. But you cannot extrapolate that chronology to other parts of the solar system because the impact rates may have been different. So just getting these rocks back from Mars to date them in an absolute sense is going to be extremely interesting scientifically. But even more than that, Perseverance did strike gold in terms of the search for life by going into the river channel, Retva Vallis. It found on one end of it a sample that became known as Chiava Falls, and Here is Perseverance standing proudly in front of the drill hole that it cored in order to collect this material. And this is one of the most intriguing samples that have been collected by Perseverance. And it's intriguing because there are in this rock, and this is now a close-up image on the scale of millimeters from the rover, there's in this rock indications of organic material. There's calcium sulfate alternating with the mineral hematite, which indicates that water was present in this material for some time. And most intriguingly, there are these little leopard spots, which are these white patches surrounded by dark rims that contain minerals that have phosphates and sulfides in them, phosphorus and sulfur-containing minerals, which are spatially separated in these rims from the rest of the leopard spot. They're concentrated. And in rocks of similar age on the Earth, those kinds of features are associated with microbial metabolism. They're associated with microbes extracting energy, chemical energy from the rock. Now, does this prove that there was life there? Absolutely not. There are other ways to have that kind of segregation occur, although they typically require higher temperatures than what this rock seems to have been subjected to. But we just won't know the answer until we bring that sample back to the Earth and it is analyzed in a laboratory like that. And they will be, that and 30 other samples, we hope will be brought back one day. These are the sample tubes themselves. This is the actual size. It doesn't look like a lot of material, but it's actually an enormous amount for geochemical labs like those that you have here at UCLA. And the demonstration of the power of doing the analysis here on the Earth comes from the analysis of samples of the asteroid Bennu by the OSIRIS-REx mission, which was a Goddard spaceflight mission led by Dante Lauretta at the University of Arizona, and I'm sure there were people here involved in it. Those samples were brought back and analyzed in terrestrial laboratories, and what was found, among other things, was about 12 or maybe 13 of the 20 or 22 amino acids that are used in biology on the Earth, and all 5 of the nucleic acid bases that are used in DNA and RNA. So amino acids are the monomers in the protein chains, and nucleic acid bases are the information containing components in DNA and RNA. And were these biological? Well, probably not, because if the amino acids were produced by biology, we might expect that they would have all either left-handed or right-handed form. They're not spherically symmetric. They're not symmetric in the sense that you could take 2 hands and superimpose them. You can see that if I put my left hand over my right, I can't superpose my thumb. I can only do it if I reverse them. That's called chiral symmetry. And amino acids have chiral symmetry, and our amino acids are almost entirely left-handed. These amino acids are 50-50 left and right-handed, and that strongly suggests that they were produced by abiotic processes. Could these have been detected in situ on Mars? If they had been on Mars in the abundance that they were detected by the analyses of the OSIRIS-REx samples on the Earth, if they had been on Mars, could they have been detected there by the instruments we have on Mars? And the answer is no. It turns out that the abundances of these amino acids range from about 5 to 750 parts per billion. The in situ instrument on the Curiosity rover, which you saw earlier, is limited to about a part per million for amino acids. And so an in situ analysis with the kinds of instruments we can carry to Mars today would not have seen any of these amino acids, nor, even if they had seen them, would it have been possible to determine their handedness. So we absolutely need to bring these samples back. And the reason I'm making this point is that the mission to bring those samples back to Earth currently is in limbo. And those samples are sitting on the Perseverance rover, waiting to be brought back to the Earth. And when they are, it will be a revolution in our understanding of the history of Mars, as well as whether life might have actually gotten started there on the Mars surface. So I want to go on now to, very, very quickly, to ocean worlds. These are bodies in the outer solar system, moons around Jupiter and Saturn, and they're moons that have liquid water underneath their icy surfaces. They're places that are probably too distant to bring samples back from, at least with the technology that we can imagine in the coming decades. But we can learn a lot by going there. And so the first of these objects I want to talk about is Jupiter's moon Europa, which is shown here in correct size relative to our moon. So it's a lunar-sized object. It's mostly made of rock, like the moon, but it has a layer about 200 kilometers thick of water surrounding that rock. And much of that water appears to be in liquid form. That is, there is a sandwich of water ice on top, liquid water, and then rock underneath. We know that from the density of Europa, its mass over volume, and we know it from something else, which I'll get to in a minute. The amount of water that is in liquid form on Europa is compared here to the Earth, taking all of the Earth's oceans and turning it into a giant cosmic dewdrop here. If we do the same with Europa, you see that potentially there's twice as much liquid water in the interior of Europa as there is in the Earth's oceans. That's a lot of volume for very big whales, if there are any. So again, what we know of Europa from measurements of the mass distribution and the density say that it's a body that has a rocky interior mostly, that's the purple, maybe a metallic core, surrounded the rocky part by this liquid water ocean, and then on the surface entirely ice. So the surface certainly is heavily fractured and looks like the crust is relatively thin. If we do a diagram of a sort of a cross section, this is what Europa's outer 200 kilometers might look like with the rock underneath and the water ice floating on top. But what really tells us that there might be a liquid water ocean is not imaging, but rather magnetometry. And this is an experiment that was actually led, and the discoveries were analyzed right here at UCLA by Margie Kivelson, Professor Margie Kivelson, and her colleagues back in the late 1980s when this magnetometer device for measuring magnetic fields was flown to Jupiter and flown into orbit on the Galileo orbiter. And the Galileo orbiter had this magnetometer. Jupiter has a magnetic field like that of the Earth. It's much more powerful. It's about 20,000 times the field strength of the Earth. That field, like the Earth's magnetic field, has an axis of symmetry that is tilted by a few degrees relative to the rotation axis of Jupiter. And so, I hope this isn't making you sick, but the field lines, as you can see, are bobbing up and down relative to the equatorial plane of Jupiter. And that equatorial plane is where Jupiter's moon Europa orbits, right along the equator of Jupiter. And so as a consequence, Europa feels this magnetic field that is varying with time as the field lines bob up and down. Now, if you've taken electromagnetism, and I'm sure everyone here has, you know that if you have a varying magnetic field that's passing through a conductor, that varying field will generate what are called eddy currents, electrical currents, which in turn generate a secondary magnetic field, an induced magnetic field, and that's a way to determine if there's an electrical conductor. And that was exactly what Professor Kivelson and her team did with multiple flybys of Europa by the Galileo spacecraft, and they found a rather respectable induced magnetic field that had a geometry that requires that the conductor not be an iron core deep down in the interior, but actually be a liquid water layer relatively close to the surface. And that is how the presence of the ocean is inferred. So there's lots of evidence for melting on Europa's surface. This is an image from the Juno spacecraft, which is in orbit around Jupiter. This is an area which has a morphology, a shape, and a topography suggestive of crustal melting, so there may be salts present. There's an area here where along this ridge or this fracture there are dark spots which might be material coming up from the ocean that's being darkened by the radiation environment around Europa. This is a similar image from the Galileo spacecraft. So Juno is still there right now. Galileo is from the 1990s. So there are all these sort of indications that there might be ocean material welling up onto the surface into this intense radiation environment at the surface of Europa. But to really find out if there's ocean material and what that material is made of requires going back with a more powerful spacecraft. And so this is a mission, the Europa Clipper, that was launched a year ago to Jupiter. It's a large spacecraft. This antenna is about 4 meters top to bottom. It is a solar-powered spacecraft, largest solar-powered spacecraft, extending about the size of a tennis court or basketball court. I forget which court. A sports court. But it's very large. You can see that. And it is packed with instruments that will observe Europa from flybys. It will orbit Jupiter. It will fly by Europa about 50 times and tell us whether an ocean is present. Now, there's a lot of bureaucracy in being the chief scientist at JPL, but one of the cool things you occasionally get to do is you get to stand next to very big rockets. And so this is the launch vehicle for Europa Clipper. It's a SpaceX Falcon Heavy. Europa Clipper's up here, and I'm down there. There's no fuel in this rocket, so I'm not being as gutsy as it looks, despite the danger sign. And then when they fuel it up, away we go.
And here we go.
You minus 15 seconds and counting.
And here we go.
7, 6, 5,
10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. And liftoff. Liftoff of Falcon Heavy with Europa Clipper, unveiling the mysteries of an enormous ocean lurking beneath the icy crust of Jupiter's moon,
So
Europa.
20 years of
Engine chamber pressures are nominal.
building all this stuff. rise
See
on
that
top
the
of
chamber
rise.
pressures are fine as we hear. All 27 Merlin engines look great.
Rocket beginning to roll, putting down
Once they
5.1
do,
million pounds of
it's time
thrust.
to
You minus.
kick the vehicle off. There's from a camera on the SpaceX rocket,
Europa Clipper.
There's Europa.
Separation confirmed.
Clipper.
And
it's
there
on
you
its way to
go,
Europa, and the
NASA's
solar panels
Europa
are
Clipper
folded
probe,
up accordion
embarking
style.
on a long-awaited mission to
And
study
it's now on
Jupiter's
its
icy
way.
moon,
And
Europa.
after a flyby
And
of
what a
Mars that it
sight,
did
man.
last year and another of the Earth, to get momentum, it will end up at Jupiter in 2030, and it will make these flybys. Europa is the blue moon that's orbiting there, and you see from Jupiter orbit that Europa Clipper in purple will be making these multiple flybys, about 49 of them, covering the surface in this very, very nice network. So we're looking forward to understanding what's in the ocean. In the meantime, it is known what is in the ocean of another moon in the outer solar system, and that is Enceladus. Now, Enceladus is a much smaller moon than Europa. That's the actual size relative to the Earth's moon. And given its small size, small bodies cool off more quickly than big bodies do. It wasn't thought that there would be much in the way of activity at Enceladus. But the Cassini mission, which is another JPL mission that was launched in 1997, actually discovered quite the opposite. Enceladus is a very active moon. So Cassini-Huygens, which dropped a probe off at Saturn's giant moon Titan, is a mission that I was involved in as a scientist for 30 years. It has lots of interesting statistics. It was, I think, one of the most successful planetary missions of all time. And one of the things that it did was to discover that this tiny moon, 500 kilometers across, 300 miles across, had at its south pole a plume of gas and ice pouring out of the south pole into Saturn orbit to make a nice ring, the E-ring. Coming out of these fractures, the plume itself resolves into individual jets that kind of look like spotlights at a rock concert. And if you get really close to Enceladus, you see that these fracture patterns break up into secondary and tertiary features from which this material comes from. Now, Cassini carried instruments that could directly sense the material in the plume. And as soon as it was discovered and determined that it was safe to actually fly through the plume, Cassini's orbit was adjusted around Saturn to make 12 fly-throughs of the plume. And the primary instruments that made the compositional measurements of the plume material are called mass spectrometers. And mass spectrometers separate chemical species by mass. And the way they do that is that these atoms or molecules that are ingested into the instrument are ionized. Electrons are separated from them. In the case of the Cassini instruments, literally by collision as the spacecraft moves at high speed through the plume of Enceladus. And then for one of the instruments, which is a quadrupole mass spectrometer, the guts of it is this set of 4 electrically conducting rods. Electric fields are modulated in these rods to steer molecules or atoms, remember now they're ions, of particular mass or weight through the tube so that they can then be detected. And you scan through all these masses, and depending upon the particular electric field you're modulating, you determine what the mass of the atom or molecule is. And from that, Cassini discovered an enormous number of interesting things. First of all, that the ice or the dust is in fact water, but it's salty water. So here's a mass spectrum. The bottom part here is blown up so that you can see the peaks. And so this is amplitude, this is mass, this is atomic mass. So water is 18, carbon would be 12. So the peaks here are seen are potassium ions and sodium ions complex with water and chlorine. And so this is all salty material. And so in fact, in the interior of Enceladus is salty material that is embedded with the ice. But the question is this part of a liquid water ocean under the surface? So Enceladus, like Europa, has an icy surface, a primarily rocky interior, but is there an ocean in between? Well, one way to determine that answer from Cassini was to observe what's called the libration, or the rocking motion, of Enceladus as it orbits around Saturn. So Enceladus is in a non-circular orbit, an egg-shaped orbit, and as it moves around Saturn, on average it keeps one face towards Saturn, but because it's in this non-circular orbit, sometimes it speeds up close to Saturn, sometimes it slows down. So it nods back and forth, and that nodding motion allows for a torque from Saturn to move Enceladus back and forth even more, to increase the libration amplitude. The amplitude of the libration, so this is not Enceladus, by the way, this is the Earth's moon over a month, so the Earth's moon also librates. So the amplitude of that libration is large enough that it suggests that the outer ice shell is separated from the interior by something that is relatively frictionless, allowing the ice shell to slide back and forth. And that indicates the presence of an ocean. And there's other evidence as well. So what else is in the ocean? Well, there are organic molecules. So here's another graph from one of the mass spectrometers. This is the signal, and the masses are actually shown, they're labeled here in peaks. And if you look at these peaks out here, they're separated by about 12 or 13 atomic mass units, which corresponds to carbon or carbon-hydrogen. And that's a strong indication that there are carbon-bearing or organic molecules. There's also silicon dioxide, which is shown here in another mass spectrum. You're all getting a course in mass spectrometry. So here's amplitude, and now the masses are not shown, but this corresponds to oxygen. This peak corresponds to silicon. It's a 2-to-1 ratio, so silicon dioxide. That suggests that the rock is being exposed to warm water, and the silicon dioxide is being leached out and in fact is reacting, the minerals are reacting with the water to produce the silicon dioxide, leaching that material out. If that's the way the silicon dioxide is formed, then there must also be hydrogen coming off in these reactions with water. And in fact, another mass spectrometer on Cassini found this large area of molecular hydrogen centered again around the fractures. So there is in this interior active chemistry going on at the seafloor. Here's the ice crust of Enceladus with the jets. Here's the ocean that's inferred from Cassini. And the compositional data suggests that there is active chemistry going on the seafloor. There are also all the ingredients for life, the key ingredients, including phosphorus, maybe not sulfur, haven't detected that yet. Phosphorus is crucial in the molecules that are the information carriers in our cells, RNA and DNA. Also crucial in the energy-carrying molecules, ATP and ADP. And in another mass spectrum, and this is, I promise you, the last mass spectrum I will show you, there are phosphorus compounds. There's a phosphate, another one, and another one. So this ocean in this tiny moon contains all the basic ingredients of life, but we don't know if life actually exists there or not. To understand whether it does, we could bring a sample back, but this is Saturn is 1 billion miles away. It's kind of far away. But we can send more advanced instruments, life detection instruments, to go beyond what Cassini did. And this conceptual diagram is a kind of a ladder of life, going from basic measurements of whether the ocean can support life, which I believe Cassini has shown for Enceladus, to more general indicators of the existence of life, isotopic evidence, to measurement of actual components of life, the fragments, the amino acids, the fatty acids, ultimately more difficult measurements of whether DNA and proteins are present, and on up from there. The next step after Cassini, which got us about here to habitability, would be advanced mass spectrometers that could make measurements, again, just flying through the plume of Enceladus, but more advanced than the ones on Cassini, that could actually detect the components of life and tell us whether they are of biological origin or not. So I want to close this little tour by going back to Mars. And I know I've thrown a lot of science at you, and I apologize, but science, as we all know, is good for you. It's good for me, at least. I want to step back from the science part for a moment to the wonder part. It's all too easy to get jaded about things that are done that are extraordinarily difficult, but we're not exposed to that difficulty day to day. And in my career as a scientist, and it's mostly been as an academic scientist, I have seen how difficult space exploration really is. We know that's true in terms of human spaceflight. We've seen the cost of human spaceflight in terms of lives. But it's also true for robotic missions. Robotic missions go where humans cannot yet go, and they go to incredibly difficult places, and they do amazing things. So here's one of those amazing things. This is an image taken from about 40 feet above the surface of that delta fan, and you can see this crater here, which is the crater Belva. That is that 1 kilometer size crater. And there's the Perseverance rover. And this is an image taken by the helicopter that Perseverance carried with it to the surface of Mars. Now, you can see the shadow of the helicopter right there. You can, of course, see the wheel on that side. The air on Mars has a density equivalent to the air at 90,000 feet above the surface of the Earth. Okay, airplanes fly at 30,000 feet. For even this tiny helicopter, about this size, very lightweight to fly, required rotor blades that moved 8 times faster than normal helicopter blades do on the Earth. The tips of those blades had to be designed so that they wouldn't cross the sound barrier at the tips, speed of sound, and generate shock waves. And this helicopter flew 70 times, even though it was designed for 5 flights. It became a scout for the Perseverance rover. Whoops. It became a scout for the Perseverance rover, which you can see up there. It scouted out interesting rocks to sample. In this are human hands and human brains. This is all human beings designing and building these marvelous robots, human beings sending up the commands. Perseverance was partly autonomous. It is partly autonomous. It can avoid obstacles, but it still requires human beings to send up the programming to tell it where to actually go. And this is on a frontier that really, I think, to be honest, humans are not going to be at for many decades to come, if ever. But we are there today through the eyes and instruments of these robots. And what they're doing is pure exploration for the purpose of science, to understand what is in our cosmic neighborhood and whether or not we are alone in that cosmic neighborhood. And I think Carl Sagan put it best in The Demon-Haunted World when he talked about what makes science a unique endeavor, that in its passion for framing testable hypotheses, in its search for definitive experiments that confirm or deny ideas, in the vigor of its substantive debates, and in its willingness to abandon ideas that have been found wanting, science is really a remarkably rare kind of human endeavor. And it's the marriage of that human endeavor with the spirit and adventure of exploration that is embodied in these kinds of missions that I've been talking about this evening. Thank you.
We may have to move you a little bit, because so if you have any questions, please use the QR code.
Here, can you move over a little bit? Okay. So Jonathan, I'll start off. Given your talk and the last few slides that you were showing, I'm wondering if all the panelists could talk about the last time that they experienced wonder in this search for life that we're on.
Yeah, so wonder for me, so I work in a very different field. So I work on exoplanets, planets around other stars. For me, a big moment of wonder scientifically was when we for the first time got some data from the James Webb Space Telescope, and it was like nothing we had ever seen before in terms of quality. And I remember my students and I digging through the data for the first time, data that no one has ever seen before, and we're seeing this huge signature of CO2 on this exoplanet. That was for me really a big wonder, yeah.
Yeah, I think I experience that wonder almost every day, even today just in the talk. These images, for example, from Enceladus, that we can see other objects in our solar system having these geysers that contain water. It blows my mind that we can study these worlds. And I also study extrasolar planets, and just seeing the diversity and richness that the universe has given us and worlds to explore. I think it's so unimaginable, wonderful, and it's so many interesting scientific challenges and questions that, it's like a miracle every day. I think it's fascinating, even like the things we can do and the the diversity we have to explore.
So I won't say the last time, but I'll say the best time for me. How's that? So the best time was 20 years ago when the Huygens probe was delivered by Cassini to Titan, and it landed on Titan. And I was with the team, the camera team, that was, we were in the European Space Operations Center, but we were actually in a trailer in the parking lot, so we're isolated from everyone else. And the first images came back, and there were only 20 of us in that trailer. And Titan is a moon with an atmosphere, and the haziness of the atmosphere prevents imaging from being done from orbit, essentially. So these images from this descending probe were the first time that anyone had ever seen the surface of this moon very, very clearly. And there were gullies carved by liquid methane and all sorts of other cool stuff. For about an hour or an hour and a half, we were the only human beings who knew what the surface of Titan looked like, because we're out in this parking lot in this trailer putting these pictures together. And then finally other people from the project found us and the spell was broken.
To me, one of the great moments of wonder was when we got the results back from the NASA Kepler mission. Kepler quantified how many planets are out there and how many potentially habitable planets there are out there. And on the basis of Kepler data, about 10 years ago, we figured out that there's something like 10 billion potentially habitable planets in our galaxy. And that number just blew my mind. And if you extrapolate that to all the galaxies out there, there's hundreds of billions of galaxies out there. There's an analogy that you can make that the number of planets in the observable universe is comparable to the number of grains of dry sand on all the beaches on Earth. It's an extraordinary number, and that just fills me with wonder every single time I think about it.
And I guess I'll close by saying I work on the Mars 2020 rover, which Ranga has on the screen, and I'd say one of the greatest moments of wonder was when I started working on the RIMFAX subsurface radar and getting the radargrams back. So our data is quite small, so we get our data back rather quickly. And with the radar, we're able to image the subsurface, and we're able to see down more than 100 feet. And so driving along the margin unit, which Jonathan talked about at the start of Jezero Crater, and being able to see major structures that look like an ancient delta in the subsurface was just a really exciting moment. And I'll just say that my background is in geomicrobiology, so looking in the subsurface, but at the micro scale, and just for folks from that perspective, potential biosignatures that we look for at the micro scale are really focused on detecting organics, which Jonathan mentioned, as well as specific minerals, which you also heard about in the talk, specific macrostructures and textures within the rock, which Jonathan also mentioned, and really the chemistry and the mapping of the chemistry, as well as isotopes and microstructures and textures. So that requires fine scale imaging.
So I want to emphasize that Emily is a real Mars scientist. I don't actually work on Mars 2020, so I'm a Mars acolyte, actually. I work in the outer, so that's your Mars scientist. Okay.
But here's the paper, and if you're interested in learning more about, I think Jonathan did a great job talking about our exciting results, the leopard spots, which you can see here, and the nodules that we detected, as well as these micro-scale reaction fronts, as well as the detection of a diversity of carbon compounds there. And so, yeah, thank you. So now we'll have Bjorn
I can
talk a little bit more.
about my research also, and it connects actually to what Jean-Luc mentioned. So this is the solar system in a kind of simplified form. But what you can basically see, there are these 4 large giant planets and 4 small rocky planets. And if you had asked me 10 years ago, 15 years ago, we would have thought, okay, this is what we should find around other stars as well. But then Kepler came. So this is what Jean-Luc mentioned. And can you go to the next? Yeah, so this is basically the main finding that the Kepler mission gave us. It told us how many planets exist as a function of size. And we would have expected that we have the large planets like Jupiter and Saturn and Uranus and Neptune, and we have rocky planets around other stars as well. But what we actually found is that the most common type of planet doesn't even exist in the solar system. So there's a big peak in the middle there, the sub-Neptunes. This is the most common type of planet. And we don't have any example like this in the solar system. So that is one of the big revelations of the Kepler mission. And what my research is actually doing is trying to understand, next slide, what we have here. So we want to understand how these planets came to be. Are they more like a small version of Neptune? Are they kind of a scaled-up version of the Earth? Or are they something completely new, like a steam world, water worlds, basically scaled-up versions of the icy moons, much bigger? And now we have James Webb, so that's on the next slide. And it gives us these amazing spectra. And in these spectra, we can see, even though we can't even see directly the planet, we can only see that the planet crosses in front of the star. At that very moment, the light from the star falls through the atmosphere, and we can analyze that light with James Webb. And it gives us this wide spectrum. And in that spectrum, from this very, very distant planet, we can see that there's methane gas. We can see there's water vapor. We can see that there's CO2 in the atmosphere. We can see that there's sulfur species in the atmosphere. So all of this, just by analyzing the light, we're doing basic remote sensing for these planets that are really far out there, as if it was a solar system planet. And so what we basically found for this particular planet is that we wanted to distinguish between these three scenarios. And what we found is that they actually, none of the scenarios that we had preconceived actually matches this particular planet. We found that it's a very different scenario. And so if you go to the next slide, we found that this planet doesn't fit our picture at all. So this picture on the left, that would be kind of a Neptune. You have a rocky core, some icy mantle, some hydrogen on top. But what we actually saw is that against expectations, against what the models predicted, is we're seeing that these two phases are actually mixed together. So that's something what we call now, sort of jokingly in the media, a vodka planet, because it's basically that the hydrogen and water, rather than being separated, they actually mix like alcohol and water is in a bottle of vodka, basically. So that's why we kind of jokingly call them vodka planets.
Okay, Björn did a great job covering sort of a great starting point to what I wanted to say. So, Björn is doing the hard part of detecting extrasolar planets and characterizing the atmospheres. I sort of spend most of my time trying to make sense of it all. No, it's very true. So the way, I mostly study the formation of planets and their evolution. So why is it relevant? Why am I even here when we talk about habitability and origins of life? I think Jonathan gave us a great example with Mars, because we think Mars probably was habitable in the past, but not today anymore. So planets' habitability and maybe having life is not a fixed point in time, but changes over time. So we need to understand their evolution. And similarly, we want to understand their formation because we want to know whether we can create conditions that are suitable for life. So I often think what I do is a little bit like what we can find analogies with bird watching. Usually when you want to find a bird, and if you have it at home, you can study it in great detail or in your lab. It's like having actually a rock from Mars, bringing it back, for sure whether you have life. But if you're spotting a bird in the wild, sometimes you only saw the back tail feather, and then usually an expert can identify it, because what they usually do is they look at size, color, habitat. And I think planet formation and planetary evolution is a little bit like this. So, after the observers, after Björn has done the hard work of detecting the planet, telling me its size, telling me its spectrum, its color, I often look at the habitat or the conditions under which it should have formed, and whether that could be making it a good target for life. And one specific example I thought I'd give you is actually, I have a not as nice figure as you, but never mind. These super Earth and sub-Neptunes, you just saw this figure. This is our solar system. This is what we know about exoplanets, right? So the most common planets are anything but what we have in the solar system. A couple of Earth radii. And so we call them now super Earths, these little ones, a little bit bigger than Earth, and sub-Neptunes. There we go. And not only it's super intriguing to understand how they're formed because we don't have them, but the question is, if we have the most common planets in our galaxies today seem to be these super Earths and sub-Neptunes, and these look rocky as far as we can tell from their composition. So would there be good targets for life? And one of the surprising things that we discovered over the last years is actually, there we go, that many of these rocky planets started out looking like a sub-Neptune. So they were not born rocky, but most likely or almost certainly formed with a hydrogen-helium envelope. And then over time actually lost this envelope and turned into a world that potentially you could walk on. So one of the things that we've been thinking about is this good or bad for habitability? Would this make them extra good targets for life or terrible targets for life? Which is sort of a question that we didn't really have to worry much about in the solar system. And one of the interesting things we find is actually, Jonathan told us already, that hydrogen and magma, so basically these are very hot in the interior, interact chemically and produce water. So although these worlds here may have formed with a hydrogen-helium envelope, one thing we know for sure, that reaction, the rock reaction with the hydrogen, led to the production of a lot of water, so several oceans worth of water. And this will be retained when the hydrogen is lost. So if you ask sort of from a condition of habitability, at least water should be plenty in those planets. So that's sort of one step in sort of trying to define or trying to find a parameter space in which we can have habitable worlds. Okay, let me hand it over.
Thank you. So we've heard a lot of great information about biosignatures, the search for biological indicators of life. And now I'd like to shift the perspective a little bit and talk about expanding the search from primitive forms of life to more complex forms of life, and also from a small search volume around the sun to the entire galaxy. And that's the work that I've been doing as part of the UCLA SETI search, which is a search for technosignatures. We're searching for evidence of another civilization, another engineer out there. We're using the largest fully steerable telescope on the planet, the Green Bank telescope. And so far we've observed nearly 70,000 stars for signs of intelligence or technological activity. We've detected something like 100 million candidate signals. None of them are extraterrestrial. And I've been very fortunate to do this work with about 170 undergraduate students and 20 graduate students, one of whom is in the room here. Megan Lee is a graduate student working on SETI. It's been a fascinating enterprise. Now, there are pros and cons to search for biosignatures versus technosignatures. So let's talk about the cons first. For technosignatures, you have to make two additional assumptions. You have to assume that life has evolved from simple life to more complex life. And we don't know how rare that is. We don't know how frequent that is. But because there are so many potentially habitable worlds, it's not crazy to think that it might have happened. In addition, nature rarely does something only once. Typically, when you find some specimen in nature, you're going to find another one somewhere else. So it's possible that there are other civilizations out there. The second assumption you need to make is that they are engaging in some kind of technological activity that is detectable with our telescopes on Earth, either intentionally or unintentionally. Now, with these two additional assumptions, we have great rewards because there's four advantages that I see to technosignatures. The first one is cost. We haven't talked about cost today, but James Webb is $10 billion, Mars Sample Return is $5 billion, Europa Clipper is $5 billion. These are expensive missions. I fully support them because they're really important. But we can conduct a really robust search for technosignatures for a factor of 1,000 less. We could start a search tomorrow for searching 3 million stars, and it would cost about $1 per star. So the cost is a big advantage. The second advantage is the search volume. All of the biosignature searches that we've talked about happen in a very small bubble around the sun. And the search volume that is accessible to technosignatures is 1 million times larger. We can access the entire volume of the galaxy. That's another big advantage. Another one that I like has to do with certainty of interpretation. If we detect these interesting molecules in the atmospheres of exoplanets, we don't have complete certainty that they're related to life. They could be related to geological activity. But with technosignatures, there's some kinds of signals that we know nature cannot produce. And so if we detect these kinds of signals and can show that they were emitted beyond the solar system, we have complete certainty about the origin of these signals. And finally, there's the potential for an enormous advance in human knowledge. That's the information content of a signal. If there's another civilization out there, it's almost guaranteed that it's far more advanced than we are. And if we could detect a message and decode the information in it, we could greatly increase our knowledge of everything about the universe. Thank you.
Thank you. And with that, I'd like to ask the panel, given the diversity of potential of a range of habitable environments that we just discussed, from subsurface oceans on icy moons to thousands of exoplanets, where should we prioritize our search efforts in the next 10 years? And what's a personal favorite target that you think has been overlooked?
So, should I start?
Sure, we could go this way, that's fine, yeah, that's fine. Anyway, Eric.
I think what is in my field nice with the James Webb Space Telescope is that it's a general purpose telescope. Right? It can look wherever we want to point it. So it's not like we have to focus on one target. We can actually characterize hundreds or even thousands of targets if we want to do that. And that's what we're doing right now. So I don't think we're overlooking things. What is, of course, difficult is even having the kind of the manpower to analyze all of this, which is often what happens actually with these general purpose telescopes. Someone builds a telescope for $10 billion, but then the science is actually being done by small university groups that are working on very small budgets. And so, for example, when we are, to imagine this, so for example, there is the TRAPPIST-1 system that maybe people have heard of. It's a system of seven planets. And they are actually the limiting factor of getting all of this analyzed is actually just the manpower of paying for grad students and postdocs for a mission that is a $10 billion mission. So that's actually quite striking for me. I think it's different for other missions where there's actually a team directly dedicated to it. But on the positive side, we have this really amazing cycle with the James Webb Space Telescope and also the Hubble telescope that we basically go always for the most exciting science. So there's every year a competition where scientists from around the world are trying to propose or are proposing to do that exciting science. So I think we're not missing out on anything in that regard because we are doing the most exciting science that we can do with this device.
I second that. But I would also, I would say I don't yet have my favorite target to search for life, because I think the exciting thing is this feedback between getting new observations, trying to make sense of them, understanding what they would imply for the formation conditions or the conditions of the planet, how the chemistry. So what the amazing thing is, like Björn showed this nice spectrum for TO-type 270D. We can show that the spectrum is fully consistent with a magma ocean, so molten rock interacting with a hydrogen atmosphere. We can calculate the chemistry and we can reproduce all these features. So one of the amazing things is we can, and this is theory that was developed here at UCLA, and we can make these predictions and compare them with the data. And I think it's that feedback that is so amazingly rich and so amazingly powerful in science, because we're taking one step at a time. And so by understanding that, we are able to better define our survey, better pick our next target, and deeply learn something about what's going on inside these planets, and which are ultimately the best targets, best exoplanet targets to search for life. So, and the other thing I would like to say is I don't have a favorite target, and I think it's really important to do all three things. To look for a life in the solar system, because the only way to have certainty is to bring something back in the lab and look at it. But we also want to look for intelligence life. Of course, it would be super awesome, right? If we definitely should look, because how stupid would it be to miss it if it's out there, right? I mean, come on. And I think we need to take advantage of the exoplanets, because there's so many of them. There are more planets than stars in the universe, so we would be crazy not to look at them. And I personally are convinced that some of them have life. We just need to find them.
So in determining where to go in the search for life, I think it's very important to have subtle or even subliminal messaging available so that people remember where it is that you actually want to go. And so I hope my message is coming through to you this evening. So on the surface of Mars today, actually in two places. One place is a cache on the ground in case Perseverance should fail suddenly. The other, that's about 11 tubes. And then on Perseverance itself are about 30 some odd tubes, almost all of which are filled. One of those tubes might contain evidence for past life on Mars. Not fossils of dinosaurs, certainly, but microbial evidence. And we won't know whether that's the case until we bring them back. And so, you know, as a nation, we've already spent $2.5 billion developing this very advanced SUV-sized rover. Now we need to go the rest of the way and bring those tubes back to laboratories like here at UCLA, and that may give us the answer, at least as far as microbial life is concerned.
I'm a big proponent of searching with many different modes, because ultimately we don't know. We don't know where the evidence is coming from. And so I'm supportive of James Webb and Mars and other search modes, including searching for intelligent life. We should be on the sky all the time, right, looking for signals. I do think that one area has been neglected, and that's the area that I'm talking about. Over the past 30 years, NASA has devoted 0.007% of its appropriations to the search for technosignatures. I think we ought to redress that and have a little bit more funding for this particular search.
I just wanted to echo what Hilke and Jonathan said as well, and I think it's important to bring the samples back from Mars while we still have the Mars science team active and not in 10, 20 years. We've had this very powerful legacy of Mars rovers and Mars rover teams and this transfer of knowledge to different generations, and I am worried that we're going to lose that pending funding cuts, pending not bringing the samples back in a timely fashion. I will say that I am also very excited about Enceladus and the potential to sample the plumes. And I think that there's strong, we saw that we have already detected a number of organics, and they're easily sampleable through the plume. So thinking about these missions that we've all discussed, I think it's also important to just recognize that it takes 20, 30 years sometimes for these projects to come to life. And so really to think about the timeline of that and why it's important that funding is consistent for these planning periods, because if we have a lapse, then you could have an entire team retire and you could lose that expertise or capabilities in the engineers that build these amazing instruments. And with that, I'd like to go to a question from online. Second. For the panel, what are some techniques that you would recommend the next generation of space biologists or space scientists learn, and what skills will be of most utility in the coming years for your respective fields?
How about we start with Jean-Luc this time?
Yeah, I think I would encourage the young generation to stick to fundamentals, learn math, learn physics, learn chemistry. There's a lot of AI tools these days, but ultimately we need somebody to really understand the fundamentals and not necessarily rely entirely on AI. Somebody needs to program the AI. So that would be my suggestion.
Yeah, so I agree 100% with Jean-Luc said, and I would add biology to the physics and chemistry. So if you are an undergraduate, you want to get into science, please, major in one of the fundamental areas of sciences that will give you the foundation that you need to really go into any of these other areas, and that's very, very important. So, and best of luck for those of you who are thinking about a career in science, work hard and study well.
Yeah, I think the only thing I want to add, I agree 100%. I do think it's the fundamental science that I think are just great because they teach you how to solve problems, with a very fundamental set of realities. And I think that's such a transferable skills out of almost all life forms and other professions, actually. One thing I would like to emphasize, I feel like I got a very traditional training in theoretical physics, and I'm now learning a lot of chemistry, and I realize at least the field of exoplanets, and I think also the search for life, you added biology. I think there's maybe more and more focus also or emphasis on the interdisciplinary nature of our work, and I think maybe one thing I would add to the fundamental degree in physics or chemistry is some of the, having a strong foundation in two fields sets you up even better, because I think these processes all work together. Nature doesn't have to pick between physics and chemistry and biology, and of course they all overlap as well. So I think that's maybe one additional angle.
Yeah, I think in general, let's take STEM as a whole field. I think it wouldn't hurt if we had more people as a fraction of the population that is trained in STEM. So I think that is a very important way. It's also a way of logical argumentation, right? And it's connecting different evidence from different sides. And so especially in the planetary sciences and what we do in experiments, it's very interdisciplinary, what you already said, right? You have to understand chemistry, you have to understand the physics, you have to understand some of the biology when you go this way. And so connecting all of those is so incredibly important. When you gave your colloquium talk earlier, that's actually what I noticed. There was basically, he gave another talk on the Juno mission, and it was basically showing the different scientific discoveries that were made with the Juno mission. And it was amazing to me to see how diverse all of this is and how the scientists connected the different pieces from very different fields of science together. I think that is absolutely important. And so I think planetary sciences is particular like this because it connects all of the different sciences.
And I want to quick go back because Bjorn said STEM. We're all scientists up here. We didn't forget engineering. Engineering, someone needs to design and build these things. So science, technology, engineering, and math. Those are the fields represented by that acronym. So if you want to be an engineer, go for it and design the next generation of missions to discover life somewhere else.
I'd also want to say for any undergraduates in the room and also for the grad students, I'd really encourage you to get involved with research if you're not already, and that may be a nice way for you to maybe put all of these different disciplines into context and maybe understand why the math is so important. For some of us, maybe math did not come so easily, and seeing why it's important may motivate you to work harder to get better at that field. And then for grad students, I wanted to encourage you also to get involved with active missions. So both for audience members as well as students, frequently NASA has opportunities for members of the public to get involved, either looking at images from Mars or other targets, as well as different counts and things like that. I just wanted to,
Maybe to add something, maybe also for the parents and grandparents in the room, something that sometimes happens in let's say the school education is that, let's say physics, chemistry, all of these subjects are being taught like, okay, now we're going to study this, and you have to memorize this, and you have to know this equation, and you have to solve this, and then there's going to be a test where you are checked on whether you can solve this problem very quickly. But that kind of endeavor of discovery, of wonder, what we talked about, is completely lost usually in the classroom, right? But actually being a scientist, what is the best for us actually, is not just purely applying the rules that we have learned, but it's actually taking that new data set and trying to dig and solving this puzzle of how can this even be, or what is the data trying to tell us. So I hope that if you have younger people in your families, that you can communicate that aspect somehow to them, that science is not just something that you memorize, but it is the tool that then will allow you to be creative, to discover things, to explore and wonder about the world around you.
Yeah, the way I see it is, I also love to paint as an artist and on the side. So I find science the same way extremely creative. And I think when you're an artist, you know, your paintbrush and your paints are your tools. As a scientist, knowing the maths and knowing the physics, these equations are your tools. But it's really all about applying it and coming up and combining it in new ways. And that's the creative part of it. And I think that's what makes science so fascinating to me and appealing.
Great, thank you. And so our next question, I think this will be particularly relevant to the remote sensors. If you were a life form from Mars or Enceladus exploring the solar system, would you be able to identify life on Earth? So maybe folks who use telescopes and maybe do look back at Earth sometimes.
Yeah, so we actually have we have spectra taken from the distance from a Mars mission that looked back to Earth and produced this hemisphere averaged, so basically a spectrum of the Earth, where you can really nicely see the absorption of O2 in the atmosphere, and you can see all the different molecules that are in our atmosphere. And if you do an analysis on this, you will actually also find out that there is a lot of oxygen in our atmosphere. So in general, there's always this worry that biosignatures could be basically, or that oxygen, for example, could be created also in a different way. In the end, you have to put all the evidence together. If you looked at the Earth's transmission or emission spectrum and you looked at all of this, for me, if we found something like this on an exoplanet or multiple exoplanets, I think it would be a very, 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 very strong indication that there is a biosphere, if you put everything together. Not one molecule at a time. You cannot just say, okay, I found O2 gas, hence there is life. But I think this actually tells quite a nice story if you look at everything in combination. It is the ultimate proof that is completely unquestionable. Will there be one scientist that doubts this? Sure, there will be. So the ultimate proof, okay, you have to go there and actually find some life form, or do what Jean-Luc proposes and basically get a technosignature from it. At the same time, the way I see this also is, we have now, for the first time in human history, the ability to study all of those planets, these millions and billions of planets in the universe. And it's our generation that will find these planets that are potentially very likely to have life. And so it's also very likely that if ever, let's say the next generation or the generation after that, builds some kind of spaceship to go there, it will have been our generation that has identified these planets. Like, it's quite likely, for example, we discovered a planet that we think has volcanic activity. It's possible that this will maybe be the first target where someone sends some kind of fraction of light speed spacecraft to one day. So I cannot promise you that this will happen. This is a question of funding in the future and getting technologies right. But what I can promise you is that we have right now the technology ready to identify all of those planets, to identify all of those targets that humanity could go to once. And what I said earlier also in a conversation with one of you is that if, for example, the Portuguese had known 50 years earlier that there is America on the other side of the Atlantic, they would have sent ships much, much earlier, right? The technology was there. People just didn't know that they should go there. So we have the big advantage right now that we can remote sense, we can find these planets, we can find these objects or planets that are very, very likely to have life. And hopefully that will, in a future generation, motivate them even more, or even our generation, motivate even more to push towards going there one day.
Follow up to that. Okay. The experiment has actually been done. Carl Sagan and collaborators used the Galileo spacecraft with its mass spectrometers and cameras, etc., to figure out whether there's life on Earth. And I have to say it, the most convincing evidence was technological.
All right, and with that, let's give our panel a round of applause. And if you have any remaining questions, we have a few minutes where you can come up and talk to the panelists. Thank you all for coming tonight.
He has a question.
Jesse?